Bismillahirrahmanirrahim. Ladies and gentlemen, welcome once again. This is the 8th episode of the serial Quantitative Techniques. In the previous lecture, we were much technical, and I am sure you will have got the idea. But before just starting from the right now, the mathematics, I would like to give you a brief and smart summary of the previous lecture. In the previous lecture, we just talked about the two concepts, the population regression function and the sample regression function. And I think it is just, we will be overlapping and overemphasizing if I say that the population regression function we can't estimate because due to limited resources, time and energy and effort and whatsoever. And on the basis of sample regression function, our purpose is to estimate the regression population function. And similarly, if we are using an indirect technique, what this means, our indirect technique should be as identical towards a population regression function as possible. So for this we will be using different techniques, and how we find the values of the parameters, that are the betas, you can say the OLS estimates. So how we find these values we will estimate, and we will just start after this introduction that how we derive the values. And I have assured you that this is the only mathematics in this course. There is, do not confuse that there is no mathematics behind the other claims. There is huge mathematics and very complex and intensive mathematics, but as I said in the previous lecture, it will consume lot of time. Now the immediate question comes that why we are using and deriving intensively OLS estimator. The reason behind this is that, as we will be talking many times about the beta 1 and beta 2 hat, and we are concerned with finding the numerical values of the beta 1 hat and beta 2, so we have to learn something about the betas. So I will be deriving mathematically the formulas of the beta 1 hat and beta 2 hat, and during this derivation I will be showing that we are using the concept of derivatives, and we are also showing that we are using the concept of minimum, because from the previous lecture you have come to know that we want to minimize the residual sum of square. So if we are able to minimize the residual sum of square, we will say that our estimates are very good, and our estimated population sample regression function is a true representative of the population regression function. So what we are going to cover today, I have explained. Just look at the first slide. We will be deriving the OLS estimators mathematically, and the second is that we will be talking about assumption of CLRM. CLRM means classical linear regression model, and we will be linking the derivation and the classical linear regression model, because when we will estimate the parameters, we will estimate the betas in the sample regression function, these are based on some of the fundamental assumption. If these assumptions are not fulfilled, then the reliability of the OLS estimator, that are the beta 1 hat and the beta 2 hat, becomes questionable. So let me start from here, and I will be very simple, and I will not be skipping any of the steps, because I believe you are very good in mathematics, but still I will be going with each and every students, and I will be showing, and I am sure you will be getting that idea. So what we will start, if you remember, what is the residual term? If I write this here, that yi is equal to yi hat plus ui hat. This is the unexplained proportion, need not to write again. This is the explained, and this was the actual observed or the true value. So what this, if I write it in this way, ui hat, bring it here, ui hat, it is equal to simply yi minus yi hat. So what this means, that the residual, the missed target, you hit the target and you missed how much by the distance is the distance between the target and your hit. So yi is the target and yi hat is your hit. So the difference between this is ui hat. So we want to, as I said, we want to minimize the residual sum of square. And I am sure that you have got the idea that why we are not interested just in minimizing the sum of residual. Why we are interested toward the residual sum of square, you can learn it from the previous discussion. So if I write here that ui hat is equal to yi minus beta 1 hat minus beta 2 hat x. This is similar, this is nothing. I have replaced yi hat by beta 1 hat plus beta 2 hat xi, and it is also xi. Why there is minus when it is in the bracket and we replace the value of yi hat, the both term beta 1 hat and beta 2 hat becomes negative. For example, I would like to show this on this side. Ui hat is equal to yi minus beta 1 hat plus beta 2 hat xi. So what is ui hat is equal to yi minus beta 1 hat plus beta 2 hat xi. So, no, this is the minus. This is the minus beta 2 hat, because minus is outside the bracket, and when we multiply this becomes plus minus becomes negative. So this is minus sign. So I have look at this, the same equation is now here. So now I square both of the term. So I will be writing squaring both of the term. In many statistical books you can find the simple formula, derivation of the simple formulas of the OL estimator, that are the beta 1 hat and the beta 2 hat. But why I am going in this way, that I have to show mathematically using the necessary and the sufficient condition that it is really the residual sum of square is minimized at this position. So squaring both of the sides, squaring both of the sides of the equation. So what will become? This will become ui hat square, and this will become yi minus beta 1 hat minus beta 2 hat xi whole square. And if I apply the summation on both sides, this is summation ui hat square is equal to summation yi minus beta 1 hat minus beta 2 hat xi square. Now this is our equation, that on the left hand side there is the residual sum of square, and on the other side that it is equal to the difference between the actual value and the estimated value. Both terms on the equations are similar. So what I am going to say now, I want to find the values of beta 1 and beta 2 hat that can minimize the residual sum of square. So I will be using the concept of partial correlation, partial derivatives here, because there are two parameters, beta 1 hat and beta 2 hat, and we have to take we have to find the formulas that will show that if we estimate beta 1 hat and beta 2 hat by these formulas, then the residual sum of square is minimal. So taking partial derivative with respect to beta 1 hat. So remember, now I will be taking, this is partial derivative of ui hat square with respect to beta 1 hat, and equal to, if this will 2 will come here by the power rule, summation yi minus beta 1 hat minus beta 2 hat xi, and we have to now multiply this. It is a formula that we have to multiply this term, the derivative of beta 1 hat. So if you see here, this is the beta 1 hat and its derivative is simply minus 1. I am not going into the details of the partial derivatives again. If the function is such kind, if it is here, the way how we derive it, we take the partial derivative with respect to beta 1. The power comes here of the function, and summation, this is minus 1 here, mean when we will be talking about taking partial derivative with respect to beta 2 hat, then we will be taking this term, and here I am interested in taking the partial derivative of beta 1 hat. So according to the first term, first condition of the minimum, the first derivative should be equal to 0. If you remember here, if I would like to show here that this is x, this is y, and this is a function, y is a function of x, and this is now minimum at this dy over dx should be equal to 0. So same condition is, we are taking the partial derivative and setting it equal to 0. If I divide both sides by minus 2, it will become summation yi minus beta 1 hat minus beta 2 hat xi is equal to 0. And if I apply the summation inside the bracket, this is yi is the variable, summation yi minus n beta 1 hat minus beta 2 hat summation xi, and this is equal to 0. I am sure you will be thinking about that why it has become n beta 1 hat. Beta 1 hat is a constant now, and the summation means that we are adding beta 1 hat 1 plus beta 2 hat 2 up to beta 2 hat n. If we are adding these values from beta 1 hat to beta 1 hat n values of beta 1 hat, so what will be this? Simply this will become n beta hat, beta 1 hat, n beta, that we have take summation of this n time. So this is, and when we apply the summation on the constant, if we apply the summation on this beta 1 hat, it becomes n beta hat. This shows that n time this beta 1 or the constant has been added. And here the beta 2 hat comes first, and we applied this on the that is the variable xi. So I will be going to the next slide, and it will become, again I will be writing the same equation here, summation yi minus n beta 1 hat minus beta 2 hat summation xi, and it is equal to 0. So what this means, if I keep it on this side summation yi, and it is equal to n beta 1 hat plus beta 2 hat summation xi. Nothing, only a mathematical trick. I just kept summation yi on the left hand side of the equation, and all the other terms went on the right hand side. And as we know that when we take the terms that are joint with minus or plus, their sign changes when they are on the right hand side. So this is our equation number 1. I would like to give the name to equation number 1. But here I would like to show you that at this position the second derivative is positive. The second derivative with respect to beta 1, because if it is minimum it should be positive. So I am going back and writing this equation again. This equation again. So what will be this? This will be equal to, so I write here showing the second derivative of beta 1 hat, a derivative of residual sum of square ui hat square with respect to beta 1 hat should be positive in case of minimization problem. Because it is a minimization problem, so that's why I will be taking the second derivative and I will be showing that how this is positive. If it is negative, then our whole theory becomes irrelevant, because on minimum the first derivative should be equal to 0, that we have put there, and on the minimum the second derivative should be positive. So I would be like writing the previous, this is summation ui hat square, this is the partial derivative we took already beta 1 hat, and it was equal to 2 summation yi minus beta 1 hat minus beta 2 hat xi into minus 1. And if I take the, now this is the first derivative, and you remember if y is equal to 7x square, the first derivative dy over dx is equal to 14x, and its second derivative d square y over dx square is equal to 14. So it means if we go to the higher derivatives, so we take the derivative on the previous, if first derivative, then we take the second, then third, and then keeps on going. So I will be taking the second derivative now of this, that partial square. Now this is the first derivative. इसी का मैं जब दूसरा derivative लूँगा तो it will become the second derivative, and this is summation ui hat square over summation the partial, this sign is partial, this is partial beta 1 hat, this is partial beta 1 hat, and it is now second derivative. Now look at here, if I take the second derivative, just first before taking derivative, this minus multiply here, it will become minus 2, and when I will, this is summation, and when I will take the now derivative of this term with respect to beta 1, this will become minus 1. So if I multiply the minus 1 inside the bracket to the outside, it will become 2 summation 1. So what is this? The summation, when we apply a summation on a constant, it becomes n. So 2 summation n. It means 1 is adding up n time, and it is n minus 1, n 1, and we need not write 1. So this is n. So now, is it greater than 1? Is it positive or is it negative? You can see that it is a positive. Why it is positive? This is a positive, and definitely there is some number of observation. It may be 1, 2, 3, and number of observation is positive. So this will become positive. So what we have proved by now, that on the minimum we are converging towards proving that the residual sum of square is, we are interested to find the values of the beta 1 hat and beta 2 hat that minimize the residual sum of square. So we have just accomplished our task up to beta 1 hat. So from rewriting equation 1 again, now this was the just proof. We are only concerned with here that we will take this equation further and we will be solving this. So if I take this equation and then I will write the other one. So I will write this equation that this was the summation yi, and it is equal to and this is equal to beta 1 hat plus beta 2 hat summation xi, and again I will write this is 1. Now take the again function. Now repeat the same story with respect to beta 2 hat. Then we will come with the second equation and then we will be able to solve it. And I will be also showing taking both the derivative. Now I will be taking the derivative with respect to beta 2 hat. So what was our equation? Our equation was that the summation, the residual sum of square is equal to summation yi minus beta 1 hat minus beta 2 hat xi square. If you remember, this is, you can find it here. This is this again here. This one I have rewritten it, and now I will be taking derivative with respect to the beta 2 hat. So taking partial derivative with respect to now beta 2 hat. Simply same the procedure. Partial derivative of residual sum of square with respect to beta 2 hat. Now the same will be 2 summation yi minus beta 1 hat minus beta 2 hat xi, and into we have to multiply again from this term here term the derivative of beta 2 hat. When we will be taking the derivative of beta 2 hat, this will become constant xi, and now it is the coefficient of beta 2 hat. So this is minus xi, minus this sign, and this is coefficient. For example, y is equal to x1 x2. So what we take dy over dx, that is the partial derivative of y with respect to x1. Now look at this. This become constant and this become coefficient of this, and this is x2. So on the same basis, why we multiplied at the end here this term, this is the formula, and you should go through the formulas. So you know we have taken the first derivative, it should be equal to 0 because it is the first and necessary condition of a minimization of the problem. So if I will multiply the xi into inside the bracket. So if I take this minus, I multiply this minus by here, this will become minus 2 summation xi multiply inside this. This will become xi yi minus beta 1 hat xi minus beta 2 hat xi square, xi multiplied by. Now you will be thinking, and I am sure you will be thinking, that why I have not divided both side of the equation by minus 2 xi so that I get rid of xi. Xi is a variable and we do not want to get rid of this, so we have to include. That's why I multiplied this xi within the bracket. So this is, now I have to prove this is equal to 0. Now I divide both sides of the term. I will divide this and I say that this equation is A. Now I have to prove, I will just take the derivative from here. Now I have to prove that this is the second derivative should be positive. So the second partial derivative summation ui hat square with respect to, now I am sure you are beta 2 hat square. Now from this you can take the derivative, this will become minus 2 and summation, and you are interested in taking the partial derivative of beta 2 hat. Again come here. This will, now this xi square will become constant and it will be considered as the coefficient of beta 2 hat. So it will become minus xi square. The similar we did here. So whether it goes to, it is now minus 2, I multiply minus here from there, this will become, and this is summation xi square. Now look at this, this is the positive, and square of anything can never be negative. Xi square will definitely be positive, and when there are observation, definitely when we will take the minus and plus observation square, it will not convert towards the 0. So this is greater than 0 and this is positive. So we have proved that the second derivative of the parameter beta 2 hat, the second derivative of the residual of sum of square with respect to the second parameter, that is the beta 2 hat, it is greater than 0. So it means we are at the point of minimum. So I would rewrite the equation A again, and this is equal to minus 2 summation xi yi minus beta 1 hat xi minus beta 2 hat xi square, and it is equal to 0. If you go to the previous slide, that this is minus 2 and this is equal to 0 to avoid any of the complication at later stage. So now I divide both of the term, both of the equations of the sides of the equation by minus 2 to get rid of minus 2. So this will dividing, you will be writing dividing. It is very simple. You need this, you need not to write this, but I am just, because you may not confuse with any of the concept. Dividing both sides by minus 2. So this will become summation xi yi minus beta 1 hat xi minus beta 2 hat xi square, and this is equal to 0. Now applying the summation, applying the summation. So this will become summation xi yi minus beta 1 hat summation xi minus beta 2 hat summation xi square, and it is equal to 0. Now I will just keep this term on left side. Summation xi yi is equal to beta 1 hat summation xi plus beta 2 hat summation xi square. So this is our second equation. There was first equation and this is our second equation, that summation xi y is equal to beta 1 hat summation xi plus beta 2 hat summation xi square. So rewriting equation 1. Now going to the next slide. Rewriting equation 1. You can go back and see what is the this was summation yi is equal to n beta 1 hat plus beta 2 hat summation xi. Now if I divide both sides by n, now I am very near towards the finding the formula for beta 1 hat. So dividing both sides by n. This will become summation yi over n is equal to, this will become n beta 1 hat divided by n plus beta 2 hat summation xi over n. Now this is very interesting here. Summation yi means we are adding up all the observations and dividing it by n, number of observation. And I think you know that if we add up all the observation and divide them by the number of observation, it becomes simply the mean. And we denote mean by bar, so this I can write it y bar because this is the mean. And this will become, this will cancel out with this will become beta 1 hat plus beta 2 hat x bar on the same footage, because this is summation xi. You are adding up all the value. Xi means x1, x2 up to xn, and if you divide it by n, it becomes x bar, the mean of the x, and here it is the mean of the y. So if now I am in a position that beta 1 hat, keep beta 1 hat here, and it is equal to, now bring this to this side, this side, this will, beta 1 hat will be equal to y bar, this will, and this term will go there and get be minus beta 2 hat x bar. So this is the formula, the simplest formula for the measuring the beta 1 hat. So this is as the simplest formula that this shows that if we will estimate beta 1 hat in this way, it will minimize the residual sum of the square. I am not going to again repeat the same things, because we have proved that during this process we put the first derivative of the beta 1 of the residual sum of the square with respect to beta 1 equal to 0, beta 1 hat equal to 0, and then we showed that at the same point the second derivative of the residual sum of the square with respect to first parameter, that was the beta 1 hat, was greater than 0, that was the positive. So that was the sufficient condition for a minima. So this is the formula for the beta 1 hat. Now we have found the formula of the beta 1 hat. Now from this we can find the values of the beta 2 hat. So writing the equation 2 again. So what is the equation 2? And I would give the name it, this is equation 3. Because when I will be asking that add up, add, subtract, and what kind of thing, we will have some symbol, and we will be going towards this 3 or 2 or 1. Now we are at the end of this derivation, and there is a bit now a difficulty as the equation has become a bit expanded, and you should be very careful in taking this. So I would like to rewrite the equation 2. Here this is the, where is the equation 2? This is the equation 2. I would rewrite this one at this. That is summation xi yi is equal to beta 1 hat summation xi plus beta 2 hat summation xi square. Now we have found the values of beta 1 hat, and what is the value of the beta 1 hat? Beta 1 hat is equal to y bar minus beta 2 hat x bar. Now we simply substitute this value into beta 1 hat. One parameter will be over. We will have the equation with the parameter that is only the beta 2 hat, and when we will solve this, we will come up with some of the formula of the beta 2 hat. Now there is no derivatives. So now there is only simple algebraic expression, and we will be doing this. So putting value of beta 1 hat in above equation. into the above equation. What this? So simply you should be a bit quick. Summation xi yi is equal to, now substitute the value of beta 1. What is the value of y bar minus beta 2 hat x bar, and this is replaced by beta 1 hat, and this is summation xi plus beta 2 hat summation xi square. Now I will be just playing very simple mathematical tricks, so I can write it summation xi yi is equal to summation yi over n. If you remember that we wrote that summation yi over n is equal to y bar. So I am taking it back to in that situation, and on the same footings it will be beta 2 hat summation xi over n, as we showed that the summation xi over n is equal to x bar. So we have replaced the values of the x bar. X bar we have replaced with this value, and y bar we have replaced with this value, and here is summation xi plus beta 2 hat summation xi square. Now what we do, we multiply this summation xi into within the bracket. So this will become summation xi yi is equal to summation xi multiply inside this summation xi summation yi over n. I have did nothing, मैंने यहाँ इसको इससे मल्टीप्लाई कर दिया, माइनस बीटा 2 hat summation xi whole square, because summation xi, this one, this is summation xi multiplied by this summation xi, this with this will become square, and it has also in the denominator n plus beta 2 hat summation xi square. So what this means, now I again go one step further. I want to take this value onto the left hand side. This will become summation xi yi minus this value, summation xi summation yi over n summation xi over this is n is equal to, now this I would like to write this term first and this term in the second, so the minus goes in the second term. I am doing nothing, but this is on the left hand side of the equation now, and here are these two terms, this one, and I am writing it that beta 2 hat, it means I am skipping a very simple step. Beta 2 hat summation xi square minus beta 2 hat summation xi whole square, this one term. Now taking LCM on both sides, and this has also, I think this has its denominator, it has n in its denominator. So what I am doing, I am going to take the LCM of both, and taking LCM, this term will become n summation xi yi minus summation xi yi all over by n. I think it is simple because its denominator is 1, and when we take the LCM, this is the situation, and here is also, this is equal to taking LCM of this with this its denominator is 1, it will become n beta 2 hat summation xi square minus beta 2 hat summation xi whole square and this whole term is divided by n. Rather than just making conjecture here, I would go to the next slide and we will see. Now what I am going to do is that the n can be cancelled out from both sides. This is formula. If both the terms are, you can say I am multiplying both of the terms with n. When I will multiply this term by n, this will become, this n will vanish and this n will also vanish. So multiplying both terms by n. Multiplying both sides by n. So what this will become? This will become n summation xi yi minus summation xi summation yi this is summation xi. Look at here, this is summation xi summation yi. From here, this is, we just take the LCM, and this is, we spotted the problem at later stage that this is, the summation sign should be here. From here, this is also here. Summation xi summation yi, and it is equal to now, this is equal to n beta 2 hat summation xi square, n beta 2 hat summation xi square minus beta 2 hat summation xi whole square. So taking beta 2 hat common on from this side. So this is taking beta 2 hat common from right hand side. So what this will become, n summation xi yi minus summation xi summation yi is equal to beta 2 hat, that is now common, and inside there is n summation xi square minus summation xi whole square. So if I take the beta 2 hat here, now I have come up with the formulas of beta 2 hat. It will become n summation xi yi minus summation xi summation yi divided by n summation xi square minus summation xi whole square. And at the same time, let me write the formula of beta 1 hat. Beta 1 hat was equal to y bar minus beta 2 hat x bar. So now we have come up with the two formulas. You should remember these of the formulas, this formula and this is for the beta 1 hat. So you should remember these formulas, because we will be using these formulas extensively, and whenever in bivariate regression model I will be talking about that beta 1 is equal to, for example, 0.5, it means I have estimated beta 1 hat by this. And if I say that beta 2 hat is equal to 0.9 again, and then it means that I have estimated the beta 2 hat by this formula. I know that this was a bit complex and you will be thinking that this may be a bit irrelevant. It is not irrelevant at this stage, because as we will be talking many times about the parameters beta 1 hat and beta 2 hat, so you should be aware of at least some of the basic formulas of beta 1 hat and beta 2 hat, and this all story is called the derivation of the OL estimates. And you know, in the bivariate regression model, OLS estimates are the beta 1 hat and the beta 2 hat. So these are the formulas for this, and now I am going towards the other topic. Assumption of classical linear regression model. So these are very interesting because the formula we have derived here, this is based on some of the assumption. If the assumptions are fulfilled, then it will minimize the residual sum of the square and it will be a very good measure. But if the sum of the assumption are lapsed, then we can't say that in this situation it has potential or it will be again very efficient, or you can say very good. Our objective is to estimate beta 1 and beta 2 that are the population parameter. Yes, our objective will remain that we are interested to study the population, not the sample. But why we take the sample? We can't study the population as a whole. So these are the parameters of the population. These are population parameter, and we applied the method of OLS. This does this job. This does this job means that it is not directly can estimate the beta 1 and beta 2, but it can measure the beta 1 hat and beta 2 hat that are from the sample. What is our what we will be thinking, that the beta 1 hat and beta 2 hat, that you have taken just the formula here. Now you may have some of the numerical value. It may have 0.4, it may have, for example, 10. I am supposing this. So now what we are looking for this, we are looking that beta 1 hat and beta 2 are how near to their counterparts. Beta 1 hat is, look at here, I will be just drawing a very, that how it is near to this one and how it is near to this one, and how this yi hat that you have estimated, this is the sample mean and this is the population mean, and how it is near to that one. Because just if we estimate and we say that we have the formula and we have estimated the beta 1 hat and beta 2 hat, it is not necessarily true that these are very near to the true beta hats, because when there are many samples, everyone will be coming with the different values of the beta 1 hat and the beta 2 hat, and we have to choose which one is very, very and very near to the population regression parameters. As dependent variable depends on regressor and error term. If you see here that the expected value of y given xi, it depends on two things, that the regressor, that a function of xi, plus the error term, that is the residual. So it means we are interested in looking at the behavior of the dependent variable, and it is based on two terms. The first regressor xi means x1, x2 up to xn, but here we are confining ourselves up to that this is the x1, x2 and x3. So ui, it means if expected value of y given xi depends on xi and ui, we have to study the behavior of xi and ui. In this way we will be able to portray, or we will able to find the true picture of the expected value of yi xi. That is why we have to make assumption. यही वजह है कि हमें assumption लेने पड़ते हैं. क्यों assumption लेना पड़ते हैं? क्योंकि y is depending on two terms. Look at here, this is xi and ui. So we have to know how the xi and ui are generated. If we will making some of the assumption about the xi and the ui, then we will be predicting the expected value of yi given xi. The first, now I have started the assumption. The first assumption is the model is linear in parameter. In today's discussion, in the first lecture, the lecture before this, I explained linearity in detail. So I will just see that we are interested that our model should be linear in parameter. ये non-linear in variable हो सकता है, but we are only interested that the model is linear in parameter. Linear in parameter का क्या मतलब है? That the beta 1 and beta 2 has the index or the power 1. एक के अलावा इनकी कोई और power नहीं है. You know this assumption. Now I am coming to the second assumption, that is the x values are fixed in repeated sampling. this is very interesting, that if you remember this again, I am going towards the same equation. This was x1. For example, this was the income of families. This is weekly income, and this is weekly consumption. The x1 we have fixed that it is the families who have income of 80. For example, there are 60, 65, 70 and 78. The other we have fixed that this is 120, this may be x2. So we can fix that there are many families who have weekly consumption expenditure. The families against the families who have income level of fixed is at 120. This is 100, 120, 115, 80 and 75. So if you look at there, in repeated sampling, for example, person A comes and he takes the sample. He will be taking, for example, randomly two values, 78. These are the values of the y against the x. So these are the y values. These are the 78 when xi is 80. And the other value is, for example, he takes this 75. He takes the value of 75 when x is fixed at 120. So this means in different sample, these x will be, the x values will remain fixed. The other person may come with he can take this value in his sample and this value. On this side, what will be his values? This will be x. X will be fixed at 80 and 120, and this will be the value of y, that will be now 65 and 100. So this means, this assumption, if you look at the assumption, this shows the x values are fixed in repeated sampling. We just repeated sample 2 times. We said that we took just 2 sample, but we can take n sample on the basis of our the population. So what here the assumption is that against each value of y, there is against only one value of x, and vice versa, that against one value of x that is fixed, there is only one value for the y. Although there are many value in the population against one fixed value of the x1, but in sample there is only one for one combination. Against one value of x, there will be one value of y. And how we explain this? We say that x values are fixed in repeated sampling. In other words, if I say, this can be said in simple another way. Simply I can say now the same, that the x values are fixed in repeated sampling. Now what I can say, the x is assumed to be non-stochastic, non-random, because now it is fixed. It is our assumption. We will see that why we take this assumption at later stage and what is the benefit of this. What this means is that our regression analysis is conditional regression analysis, that is conditional on the given values of the regressor. We have fixed the regressive. If you see the previous one, if you see here, we have fixed the regressor. Regressor are the independent variable. We have fixed it at x1, that is the 80, and this is the at 120. The third assumption is the zero mean value of disturbance term ui. This is very interesting, and we have proved that in the first lecture we proved that the summation or the expected value of ui is equal to 0. What this means, if I would like to write it in the notation form, it is just expected value of ui given xi, it should be equal to 0. What this means, I will be showing it through the diagrams. I was talking about the third assumption, that the zero mean value of the disturbance term. What this means, that the disturbance term is normally distributed, and technically this can be written as I wrote here, that the expected value of ui given xi is equal to 0. So what I will be saying, and I will be showing this, it can be showed in two ways. For example, this one, and this is the simple way, this is the x, this is y. What I say that at this level, the sum of residual plus residual is equal to the sum of minus residual, and their sum is equal to 0 at this stage, coming from here to here. Similarly, at this stage, I can say that again plus residual are equal to minus residual, and at each place the residual sum is equal to 0. So I can draw it with another diagram. I can make it on the same line, but I would like to draw it something differently. This is the x, this is the y. What this? For example, if now I would like to show this on this, that this is normally distribution, and you know this is the normal distribution. Normal distribution with zero mean. So what this means, if I come from here and if I reach this point, plus and below and above this residual sum is 0, again I can make this is the second norm. At each point it is normally distributed. So this is the third, is that the residual sum is equal to 0. The mean of the residual term is equal to 0. In our regression, what we say, what is this means? For example, this means as it means yi hat is equal to yi is equal to yi hat plus ui hat. Ui hat, as you know, these are the forces that are out of our model, that are the unknown forces, but they have the effect on this. When we suppose that the residual sum is 0, what we have supposed, that if this term is affecting from above this, for example, I say this is the positive residual, and this term is affecting this is below, and I say this is the minus. So what this means, there are now two opposite unknown forces. One is trying to suppress the yi, and one is trying to inflate the yi. So if I say that the plus and minus forces, plus and the minus forces are equal to 0, it means its effect become totally random. It can neither inflate our yi, it can never deflate our yi, this yi, and we will be linking it just with yi hat. So this was the logic behind that why the residual sum should be equal to 0, so that its effect is random. It is neither pushing upward the value, it is neither the suppressing the value. This was the fourth assumption, is that the homoscedasticity are equal variance of the error term. So what is the homo mean equal, and scedasticity means spread. I would like to write it here, that homo means equal, and from this scedasticity mean spread. What this means, that at each point the variance of the error term should be constant. If at one where we fix the x1, if it is 5, it should be at each x fixed values of x, it should be equal to 5. So what in mathematical notation it can be written, and in words you can say that the conditional variance of the ui. Keep in mind, I am talking about the variance about the error term, not the x or the y. So ui, its variance is identical at each stage. So symbolically we can write this, that the variance of ui given xi is equal to a constant. So what this means, I will be showing it by the diagram, and I will be showing what is the homoscedasticity and what is the heteroscedasticity. And here just you should remember that at each fixed value the variance of the error term should be identical. If at one xi it is 10, on each x1, x2, x3 it should be 10. So just look at here, I want to show this in 3D. This is f of u, this is y, this is our x, and I draw a line where I will show that what is the homoscedasticity. Due to this electronic pen, you may face that I may have some of the here. So this is normal distributed. If you see here, this is again, and you can see the spread is equal here. Every point the spread is equal. So if you see the spread here, this is the spread every time. If you call it this 1, this 2, this 3 and this 4, this will be equal. This is 1 is equal to sigma square 2, and this is equal to sigma square 3, and is equal to sigma square 4. So I would like to have some of what is the heteroscedasticity. So I would like to give, before going towards the heteroscedasticity, I would like to give you the brief summary what we have covered today. We started from the derivation of the OLS estimator, and OL estimator in the derivation we showed that if we will derive these parameters beta 1 hat and beta 2 hat, in this way we will be minimizing the residual sum of square. And we proved it with the mathematical conditions that at the minimum, the first condition should be equal to 0, the first derivative should be equal to 0, and this is the necessary condition, and the second derivative should be positive if it is minimum. And we derived the formula, and I expect and hope that you will learn this formula by heart, because we will be using again and again these formulas. Although we will not be going into the intensive mathematics in the previous the later discussion, but at least you should have well aware of these formulas. Now we went up to the assumption. We have just covered the 4 assumptions. The first thing is that why we need assumption. We need assumption because yi value depends on two things, that xi on the error term. Xi are the independent variable and ui is the residual term. If we are interested to find the true behavior of the yi, we should know that how the xi and the ui are generated. And for this we have to make some of the assumption that how xi and ui have been generated. What were these assumptions? The first assumption was that the model should be linear in parameters. So keep in mind that we are only interested in the linearity of the parameter. We are not interested in the linearity of the variable. The model may be nonlinear in the variable. The second assumption was the residual sum should be equal to 0. And what this means, that the forces that are out of our model, they should randomly affect our the dependent variable. The third assumption was that there should be homoscedasticity. What this means, that at each point that the spread at each fixed values, our residual term should be normally distributed and its spread should be equal. The second assumption was that the x values are fixed. What this means, that they, against each fixed value of x, there are many y values. But in repeated sampling, we will keep the x's fixed and we will be taking only one value. This will give us the benefit that there will be only one value of y against one fixed value of the x. So this was the story from me for today, and we will keep on discussing our regression in the later stages, and we will be doing it on the practical e-views. So thank you very much. Goodbye and Allah Hafiz.